At this moment, you feel protected. You rely on the chair beneath you to support your body. You assume the walls around you are firm, unmoving, shielding you from the outside world. But that sense of security is mistaken. What you're feeling is not safety. It's a mental projection, a soothing illusion your brain creates to keep you functional. Because if you were able to perceive reality as it truly operates, if you could strip away the familiar surface of everyday logic and expose the underlying structure, calm would be the last thing you'd feel. You would feel fear. You are not resting on something solid. You are suspended above a restless cloud of oscillating entities that are almost entirely empty space. And strangely enough, that part is reassuring. The unsettling part is this: those entities refuse to obey the rules you were taught. From childhood, we are conditioned to believe that reality is stable and well-behaved. We assume the past is sealed shut, the future lies ahead untouched, and objects exist independently of whether we observe them. But for over a century, the sharpest minds on the planet have been uncovering fractures in that narrative. Not small flaws, deep, jagged breaks that hint at something disturbing. The universe may not be rigid at all. Imagine discovering that your reflection could act before you did. Imagine learning that a choice you make tomorrow could alter the record of what happened yesterday. Imagine two people staring at the same light source, one seeing it illuminated, the other seeing darkness, and both perceptions being equally correct. This isn't speculative fiction. This is the logical consequence of quantum mechanics, and it implies that the reality you depend on might function more like a digital simulation, one that only generates detail when someone is watching. We like to believe science exists to clarify the world, but at the quantum level, clarity doesn't fade, it combusts. The instruments we've built don't merely observe reality, they interfere with it. They reveal particles that occupy multiple locations simultaneously, as if they possess perfect alibis. They expose connections that stretch across the cosmos instantly, unconcerned with the speed of light. And most unsettling of all, they point toward an idea physics has spent decades trying to avoid: that the universe may not exist in a meaningful way without an observer. So pause for a moment, take a breath, look at your hand, look around the room you're in. Does it feel solid? Does it feel permanent? Hold onto that sensation. Because over the next few hours, we're going to dismantle it piece by piece and show you exactly why Albert Einstein carried unease about these discoveries to his grave. Welcome to the paradox. You might be thinking, all right, but does any of this actually matter? It's tempting to dismiss quantum mechanics as a clever trick for mathematicians. You see a headline about particles being in two places at once and shrug it off. You tell yourself it's just abstract math or a theoretical oddity with no relevance to real life. The world you inhabit, mortgages, traffic, sports, daily routines, feels governed by firm, dependable rules. The mug on your desk doesn't care about superposition. It just sits there. But here's the uncomfortable reality. The mathematics isn't a metaphor, it's a blueprint. And every time we compare that blueprint to the physical world, the world agrees with it. This isn't chalkboard speculation anymore. We're talking about real machines. Lasers, mirrors, detectors, hardware built from silicon and metal. Over the past several decades, physicists have constructed experiments designed to corner reality, to force it to reveal whether it's lying. And every time it does. These experiments have been repeated across the globe, from elite laboratories in the United States to research centers in Europe. They've been replicated, scrutinized, verified. And their outcomes are so consistently counterintuitive that they fractured the confidence of some of the greatest thinkers in history. Einstein didn't reject quantum mechanics because he failed to grasp it. He rejected it because he understood exactly what it implied. If the equations were correct, then the universe wasn't a clean, predictable machine. It was something stranger. Something that allowed non-local connections and events that seemed to reach backward through time. He spent the final years of his life searching for a flaw, trying to prove that randomness had no place at the foundation of reality. But the experiments delivered their verdict. The randomness is real. The dice are rolling and landing on outcomes that classical logic says should be impossible. We've moved beyond asking whether this is happening. Now we're forced to confront what it means. And what it means is that the solid world you experience every day is little more than a fragile surface stretched over a turbulent, chaotic depth. So what's actually down there? To grasp the scale of the problem, we need to take this apart carefully. We're going to examine 3 specific paradoxes, 3 controlled detonations aimed directly at your common sense. No heavy jargon, just the setups, the mechanisms, and the consequences. First, we go after time. We all assume the past is fixed, finished and untouchable. What's done is done. Or so we think. The delayed choice quantum eraser experiment challenges that assumption in a way that feels almost illegal. It asks a question that shouldn't even be coherent. Can a decision made in the present alter the recorded behavior of a particle in the past? This isn't science fiction. It's a direct assault on cause and effect. Next, we dismantle space. We'll explore quantum pseudo-telepathy. In everyday life, information has to travel. You speak, text, gesture. Something moves from one place to another. Even light obeys a speed limit. But quantum mechanics permits correlation so strong, they ignore distance entirely. It suggests that 2 objects separated by vast stretches of space can behave as a single system, responding instantly without exchanging any signal at all. Distance, it turns out, may be more illusion than fact. And finally, if you're still holding on, we confront the final boss, the paradox that threatens the very idea of objective truth, Wigner's friend. It takes the famous thought experiment involving a cat and pulls it into human experience. It asks what happens when 2 observers witness the same event and arrive at mutually exclusive realities, and the mathematics insists that both are correct. This is the paradox that unsettles physicists the most. Because if facts themselves aren't universal, then what exactly are we studying? By the time we're finished, you won't just be questioning physics, you'll be questioning the floor beneath your feet. Let's begin at the foundation that organizes your entire life, time. You don't need advanced degrees to understand how time feels. You experience it constantly. It moves forward, never backward. You were younger once, now you're older. You light a match, it burns, becomes ash, and cools. You never see the process reverse. Ash doesn't reassemble into wood. Flames don't leap back onto the stick. This one-directional flow is what we call the arrow of time. It's the reason a video of a building collapsing looks natural, while footage of rubble assembling itself feels fake. This directionality is so deeply wired into our minds that we treat past and future as fundamentally different categories. The past feels permanent, recorded, settled, like a receipt you can't edit. The future feels open, uncertain, shaped by choice. That distinction underpins regret, responsibility, and hope. It's how we navigate existence. But here's the problem. The universe doesn't seem to share our intuition. When you strip reality down to its fundamentals and ignore the messy complexity of everyday life, the arrow of time simply vanishes. Newton's laws don't favor forward or backward motion. Relativity is perfectly neutral about direction. The Schrödinger equation shows no preference at all. At the deepest level, the laws of physics are symmetric in time. Record a microscopic interaction and play it in reverse, and nothing breaks. A collision between particles is just as valid backward as it is forward. The equations don't blink. They don't recognize past or future. There's no rewind, no fast forward, just movement. So here's the obvious problem. If the universe itself doesn't care about direction, why do we remember yesterday but not tomorrow? Why can't we influence events that already happened? Physicists usually answer this with entropy, the idea that disorder tends to increase. But entropy is a statistical rule. It governs large, chaotic systems. Scrambled eggs, burning fuel, broken machines. It works beautifully for big, messy objects. But when you isolate a single quantum system, a lone photon drifting through empty space, entropy no longer guards the timeline. The boundary between before and after starts to dissolve. And inside that haze, unsettling possibilities emerge. Possibilities that suggest the future may exert influence on the past just as powerfully as the past shapes the future. To understand how time itself can be destabilized, we need to revisit the most famous experiment ever performed in physics, the double slit experiment. You've probably heard of it. Maybe you encountered it in school and then promptly forgot about it. But we need to examine it again, not as a neat textbook illustration, but as a forensic investigation. Because this is where reality first slips up. Picture a machine gun firing bullets at a solid steel plate with two narrow vertical slits cut into it. Behind the plate is a wall. Most bullets are blocked, but some pass through the openings. On the wall behind, you'd expect to see two vertical clusters of bullet holes. Straightforward, predictable. That's how physical objects behave. Now shrink the bullets down to the scale of electrons or photons. Suddenly, the logic collapses. Instead of two clusters, the wall fills with a complex pattern of alternating bright and dark bands, an interference pattern. It resembles ripples on water, overlapping and canceling each other out. This pattern tells us something astonishing. The particle didn't pass through one slit or the other. It passed through both simultaneously. It behaved like a wave, splitting itself, interfering with itself, and arriving at the wall not as a single point, but as a cloud of probabilities. Here's where things turn unsettling. Place a detector at the slits, a sensor, a camera, any device capable of identifying which slit the particle passes through, and the wave behavior collapses instantly. The particle snaps into behaving like a classical object. It goes through one slit only. The interference pattern vanishes, replaced by two dull, predictable bands. Think carefully about what that means. The particle behaves differently, depending on whether it's being observed. When unobserved, it explores every possible path at once. When observed, it commits to a single outcome. The act of measurement doesn't just reveal what happened. It forces reality to choose. That alone is deeply disturbing. It suggests that the particle's history, the path it took, isn't fully defined until someone asks the question. But physicists weren't satisfied with stopping there. They asked a more dangerous question, a question that pushes straight into forbidden territory. What happens if we wait? In 1978, a legendary physicist named John Archibald Wheeler proposed a way to test just how far this strangeness goes. Wheeler, who worked alongside giants like Einstein and Bohr, devised what became known as the delayed choice experiment. His reasoning was simple and devastating. In the standard double-slit setup, we decide whether to observe the particle before it reaches the slits. Detector on, and it behaves like a particle. Detector off, and it behaves like a wave. But Wheeler asked, what if we delay the decision? What if the particle passes through the slits first, and only afterward do we decide whether to measure its path? Imagine the particle has already crossed the barrier. At that moment, it should have already chosen its nature, wave or particle. It's now traveling toward the detection screen. Only then do we flip the switch. We decide in the present how to interpret an event that has already occurred in the past. If time behaves the way we think it does, this choice shouldn't matter. The particle already made its move. The footprint is already in the sand. The past should be untouchable. But Wheeler predicted something outrageous. He argued that the particle would retroactively adjust its past behavior to match the measurement chosen in the present. If you choose to measure its path after the fact, the particle will behave as though it had always been a particle, as if it went back in time and rewrote its own history. To illustrate this, Wheeler extended the idea to cosmic scales. Imagine a single photon emitted from a distant quasar billions of light years away. On its journey to Earth, it passes around a massive galaxy whose gravity bends its path, giving the photon two possible routes, left or right. The photon travels for billions of years. It reaches our telescope today, and only now do we decide whether to measure which side of the galaxy it came from. According to Wheeler's logic, our choice today determines whether that photon traveled as a localized particle or a spread-out wave for its entire journey across the universe. Let that sink in. It suggests the universe's history isn't a finished recording. It's a live transmission, and observation is part of the editing process. For a long time, this was just a thought experiment, a terrifying implication scribbled on paper. But eventually, technology caught up. To test this idea in the lab, physicists needed a way to delay the measurement without disturbing the original particle. This led to the creation of the quantum eraser. Despite its ominous name, the quantum eraser isn't a weapon. It's an ingenious experimental setup designed to exploit the loopholes of causality itself. Here's how it works. A laser fires photons toward a double slit. Just beyond the slits, scientists place a special crystal, a beta barium borat crystal. This crystal performs a remarkable trick. Every photon that enters it is split into two entangled photons. They carry less energy, but they remain permanently linked. They are twins. One twin is called the signal photon. The other is the idler photon. The signal photon travels directly to the detection screen and leaves a mark. That mark is recorded. The event is over. History, as far as we're concerned, has been written. The idler photon, however, carries the crucial information, which slit the signal photon passed through. Because the two are entangled, knowing the idler's path reveals the signal's path as well. So the scientists send the idler on a detour. They route it through a long maze of mirrors and fiber optic cables. This delay creates a time gap. The signal photon hits the screen first. Its position is logged. Meanwhile, the idler is still traveling, and this is where the experiment crosses the line. While the idler is still in transit, after the signal photon has already been detected, the scientists make their choice. They can send the idler into a detector that preserves the path information, or they can send it through a device that scrambles and erases that information entirely. Pause the universe at this moment. The signal photon has already struck the screen at a specific location. That happened nanoseconds ago. On human timescales, that's nothing. On quantum timescales, it might as well be ancient history. The mark is fixed. It cannot move. The past appears locked. Meanwhile, the idler photon is still traveling through the optical fibers. Relative to its twin, it exists in the future. No decision has been made yet. The universe is waiting. Classical logic insists that whatever we do to the idler now should be irrelevant. The signal photon is gone. You cannot change a footprint after the foot has lifted. The pattern on the screen, wave-like or particle-like, should already be determined. But this is exactly what the quantum eraser is designed to test. Does the signal photon somehow know what will happen to its entangled twin in the future? Does the spot it left on the screen depend on a decision that hasn't occurred yet? If the answer is yes, then the chain of cause and effect is shattered. If the answer is yes, then tomorrow is reaching back into yesterday, quietly rewriting what already seemed settled. The scientists sit at the controls. The stream of results starts pouring in, and what shows up on the displays clashes with everything a rational mind expects the universe to be. So let's walk through the mechanism of the trap, because the details matter. The idler photon is racing through long fiber optic cables. Ahead of it sits a sequence of semi-transparent mirrors, beam splitters, the crossroads where the decision gets made. These are the levers that determine what kind of reality the experiment will allow you to see. Here's the structure of the choice. If the idler photon ends up at one set of detectors, call them D3 and D4, then the path information is preserved. In other words, the system retains which slit knowledge. You can tell where the photon originated. The universe has a label, a tag, a trail. The photon's history is, in principle, knowable. And in that case, you would expect the signal photon on the main detection screen to behave like a classical particle. No interference, no ripples, just a straightforward impact distribution. But there's another route. The beam splitters can be arranged so that the two possible paths are blended together so completely that the origin becomes impossible to reconstruct. Light associated with the left slit and light associated with the right slit get mixed in a way that destroys the ability to say, it came from here. If the idler is routed into detectors like D1 or D2 under that arrangement, it arrives without a traceable identity. The which path information is erased. Not hidden, not difficult, not inconvenient. Erased in the literal sense, no longer recoverable. And here's the crucial part. That erasure is not something the experimenters force by hand in advance. It's randomized. Sometimes it happens because the beam splitters route the photon one way. In more sophisticated versions, a random number generator flips the configuration at the last possible instant. The entire point is that the decision to preserve or destroy the information happens after the signal photon has already completed its journey and hit the detection screen. The signal photon is already history. The idler photon is still in flight, about to decide what kind of information will exist about that history. It's like waiting until a runner has finished the race taken a shower, and gone home, and only then deciding whether the starting gun was fired. Common sense says the outcome is locked. The race already happened, but the quantum eraser basically looks at common sense and says, "Cute, watch this." The experiment runs. More data comes in. Thousands of signal photons strike the main screen, and at first glance, it looks like nothing happened. The screen shows what looks like a messy smear, a noisy blob with no obvious structure, no clean interference fringes, no dramatic split. You could easily assume the whole setup produced nothing but randomness. But then the scientists do the one move that makes the entire thing explode. They sort the data. They take the timestamp of every signal photon and pair it with the timestamp of its entangled idler twin. Then they split the signal hits into two groups. Group A, signal photons whose idler twins ended up in the detectors that preserved witch path information. Group B, signal photons whose idler twins ended up in the detectors that erased the witch path information. Remember the order of events. The signal photon hit the screen before the idler photon reached the choice stage. When the signal landed, it had no way, in the ordinary sense, to know which group it would later be assigned to. And yet, when you examine Group A, the pattern is exactly what you'd expect from particles. A clump, no interference. When you examine Group B, the interference pattern appears. The signature wave fringes emerge cleanly. Sit with that for a moment. The signal photons whose twins would later have their identity erased behave as if they traveled like waves. The signal photons whose twins would later preserve their identity behave as if they traveled like particles. It's as if the signal photon reached the screen, waited for tomorrow's paperwork, received a memo from the future, and then chose how to behave yesterday. The data does not wobble on this point. The erased subset shows interference. The kept subset does not. A future condition determines a past description, and that result feels offensive because it attacks the deepest structure of how we interpret reality. In the everyday world, causality runs in one direction. You push a domino, that's the cause, and the fall is the effect. The cause must happen first. The effect comes after. That ordering is what we mean when we say time has a direction. But in the quantum eraser, the effect, the pattern on the signal screen, is registered before the cause, the erasure or preservation of information in the idler channel. It's like writing a note to your past self and having it already sitting on your desk yesterday. It suggests the timeline isn't a line of dominoes, it's a stretched web. Tug one corner and the vibration shows up at the other, even if, by our usual clocks, the other end is earlier. So how could a photon pull this off? Is it secretly broadcasting signals? Does it have some hidden communication device? A psychic antenna? No. It's a particle. No brain. No intention. No strategy. And yet the correlation is flawless. Every time the witch path information is erased, even if that erasure happens much later or at a vastly different location, the corresponding signal data sorts into wave behavior. Every time the information remains available, the corresponding signal data sorts into particle behavior. It's as if the universe is enforcing a strict consistency rule. You are not allowed to see wave-like interference if you also have the power, anywhere, at any time, to know the path. And notice that phrasing, it's not about when you learn it. It's about whether the information exists in principle. If the witch path information exists anywhere in spacetime, past, present, or future, then the wave description is forbidden, and the probability collapses. If the information is genuinely destroyed, interference is permitted. Now, before you start dreaming about building a time machine to alter history or harvest lottery numbers, we have to slow down. There's always a catch. When you look at the raw signal screen by itself, before you match it to the idler records, you don't see interference. You don't see a crisp particle pattern either. You see a bland gray smudge. The wave and particle subsets overlap in a way that cancels the obvious signature. You only extract the hidden structure after you bring in the idler data and separate the events. That's why you can't use this to send messages back in time. You can't stand at the signal screen, spot interference fringes, and conclude, "Ah, my colleague will erase the information tomorrow." You won't see fringes, you'll see noise. You need the future data to decode the past. You need the later key to unlock the earlier pattern. Physicists call this the no signaling principle. It's the safety rail that keeps relativity from collapsing. It prevents the obvious paradoxes, the kinds of paradoxes where you create contradictions by communicating backward. But here's the brutal part. That safety rail doesn't remove the strangeness. It only prevents you from exploiting it. You might not be able to send a usable message back in time, but the link is still there. The future event is still mathematically tied to the past event. The universe still coordinates the two ends of the timeline. It just keeps the evidence scrambled until the later information arrives. Like a perfect crime where the proof exists, but it's encrypted with a key that hasn't been generated yet. The distortion happened. You just can't read it until later shows up. So what does that imply about your life? About the story you tell yourself about time? We treat the past like a finished painting. The brush is down. The paint is dry. The trees and clouds are locked in place. History, in our minds, is a catalog of events that definitely happened in one definite way. But the quantum eraser suggests a different metaphor. It implies the past is less like a painting and more like a developing photograph, a Polaroid still forming. The image exists, but it's hazy. It's unresolved. It remains partially undefined until something in the future forces it into focus. Think about what that means. It means that an event you label as yesterday might not be a single fixed outcome at the deepest level. It might be sitting in a ghost-like state, waiting for a future interaction that finalizes what it was. That demolishes the idea of a simple linear timeline. In a linear story, A causes B, and B causes C. Here, C seems to lean backward and whisper instructions into A. The ending helps write the beginning. This is what physicists call retrocausality. It isn't Hollywood time travel. You're not stepping into a machine and changing the past directly. It's subtler than that, quieter, more disturbing. It's the idea that the timeline behaves like a taut rope. Pull one end, the other end moves. Past and future are not separate objects. They're two ends of the same structure, and consistency binds them together. When the idler photon's outcome is fixed at a later moment, it's like a pull on a stretched cable, and the earlier behavior of the signal photon responds to that pull. Reality reshapes itself to stay consistent across both points in time. So history is not a neat line of dominoes tipping forward one by one. It's a handshake that spans time itself. The past reaches toward the future, and the future reaches back toward the past. Reality only becomes concrete when those two directions meet. Until that moment of contact, everything exists as probability. Everything is haze. You may believe your past is carved into stone, but physics suggests it may simply be waiting for you to finish writing the ending. You might hope this is just an obscure idea, something most physicists quietly ignore. You might hope it's philosophical fluff, not serious science. But the truth is far less comforting. For decades, respected scientists have been constructing mathematical frameworks that describe exactly this kind of behavior. One of the most influential is known as the two-state vector formalism, developed by Yakir Aharonov, a towering figure in the foundations of quantum theory. His proposal is mathematically clean and conceptually unsettling. In conventional physics, we describe a system with a single state vector. It begins in the past and evolves forward into the future. Like an arrow released from a bow, we use past conditions to predict the present. If you know where an arrow was a second ago and how fast it was moving, you can calculate where it is now. That logic is how we launch satellites, land spacecraft, and navigate everyday life. We look backward to move forward. Aharonov argued that this picture is incomplete. According to him, a quantum system is not defined by one arrow, but two. The first behaves exactly as expected, flowing from past to future. But the second state vector does the unthinkable. It originates in the future and propagates backward toward the past. Let that idea settle for a moment. Right now, in this room, you are shaped by everything that has happened to you since the moment you were born. But under this framework, you are also being shaped by everything that will happen to you until the moment you die. The present is not a starting point or a destination. It is a collision zone, the place where influences from both directions meet. This framework dissolves the quantum eraser paradox effortlessly. Why does the signal photon behave as if it knows what the idler photon will do later, because the information is flowing backward from the future measurement. The choice made at the detectors sends a ripple back through time. That ripple reaches the signal photon and informs how it must behave to maintain consistency. In this view, nothing supernatural is happening. No mystical forces, no hidden intelligence. Just a universe that is perfectly symmetric in time, where influences move both ways along the timeline like traffic on a two-lane road. We only notice one direction because our minds are wired to read stories from beginning to end, page by page. The universe, apparently, reads the entire book at once. It's tempting to dismiss experiments from the late 20th century. To say the instruments weren't precise enough, that the lasers drifted, that the detectors weren't reliable. Skepticism is healthy. It's how science stays alive. But in this case, skepticism has run out of room to maneuver. The delayed choice experiment didn't collapse under scrutiny. It hardened. In 2007, a team led by Vincent Jacques carried out a version of the experiment precise enough to silence most remaining objections. They didn't rely on crude setups or indirect assumptions. They verified the single photon nature of the source with extreme accuracy. They closed loopholes. They eliminated alternative explanations. And the outcome remained unchanged. The future choice still dictated the past behavior. Then, in 2013, a group led by Xiaosongma pushed the experiment even further. They separated the entangled photons by enormous distances, sending them to entirely different laboratories. This ensured that no ordinary signal, not even light, could travel between them in time to coordinate the results. Atomic clocks synchronized the measurements down to nanoseconds. Every effort was made to guarantee that the choice occurred strictly after the signal event. They tried to break the effect. They tried to rescue the classical picture of time. The universe refused. The results were unmistakable. Interference appeared only when the future measurement allowed it. Particle behavior appeared only when the future measurement demanded it. The data aligned perfectly with quantum predictions. This was not noise, not a software glitch, not a statistical fluke. This is a structural feature of reality. At this point, the question is no longer whether it's true. We know it is. The real question is why we resist accepting it. Why do we cling so fiercely to the idea of a flowing, linear timeline when the evidence keeps telling us that flow may be an illusion? Perhaps because the alternative is overwhelming. If the future is real enough to send influences backward, then maybe the future already exists. And that realization leads directly to the most disturbing idea in modern physics, the block universe. If time is symmetric, and if future moments exist just as firmly as past ones, then time does not flow at all. There is no river carrying us forward. There is only a frozen structure. Imagine a loaf of bread, long, solid, unmoving. Slice it into thin sections. Each slice represents a moment in time. One slice contains the age of dinosaurs. Another holds the Roman Empire. One slice shows you eating breakfast this morning. Another contains your funeral decades from now. From inside the loaf, you experience only one slice at a time. You believe you are moving from one slice to the next. You believe the future slice doesn't exist until you reach it. The block universe says that's an illusion. The entire loaf exists simultaneously. The beginning, the middle, and the end are all equally real. They are frozen together in a four-dimensional structure we call spacetime. Dinosaurs still roam their slice. In another slice, you are already gone. Nothing is actually moving. Nothing is changing. The only thing that moves is awareness. Your consciousness slides across the block like a beam of light scanning a film reel. The movie is already complete. The script is written. The ending is fixed. You're just watching it unfold for the first time. The quantum eraser fits perfectly into this picture. It shows that the future is solid enough to reflect influence backward. It shows that tomorrow is already there, waiting. And if that's true, then free will becomes a terrifying question. When you decide to erase the path information later, did you truly choose? Or was that decision itself just another frozen feature of the block? Another line of code written before the universe ever began? This is the cost of understanding quantum mechanics. You glimpse the machinery behind reality, and in exchange, you lose the comfort of believing you're in control. You begin to suspect you're a character in a book that's already been printed. And no matter how hard you struggle on the page, the words ahead of you are already there. We have dismantled time, turned it into a cage. But if that thought feels suffocating, brace yourself. Because at least in a cage, you know where the bars are. In the next paradox, we're going to discover something even worse. The bars may not exist at all. Now we step out of the prison of time and into the vast emptiness of space. If time is the force that carries us forward, then space is what keeps us apart. We assume separation is fundamental. I am here. You are there. The screen sits in front of you. The wall stands behind you. Distance feels real, and distance feels safe. In the classical view of reality, distance is the ultimate shield. If you want to influence something, you have to touch it. If direct contact isn't possible, you have to throw something at it. Quantum mechanics is about to demolish that rule. If you can't throw a rock, you have to send a signal. A vibration in the air, a radio transmission, a beam of light. All influence must travel, and travel takes time. Nothing happens instantaneously. This principle is so fundamental that it has a name: locality. Locality was the foundation of Albert Einstein's worldview. He believed that every object's influence is confined to its immediate surroundings. Nothing in his universe could propagate faster than light. If the sun were to explode right now, we wouldn't know about it for 8 minutes. We would still see sunlight. We would still feel the gravitational pull. For those 8 minutes, we'd remain unaware, because information must physically cross 93 million miles of space to reach us. That speed limit is what keeps the universe intelligible. It prevents chaos. It guarantees that causes precede effects in an orderly chain. It implies that objects carry their own independent realities. An apple resting on a table in New York has its own properties. An apple sitting in London has its own properties. They are separate. They do not coordinate. They do not exchange secrets. They do not care about one another. They are isolated islands floating in the vast darkness of space. This idea of separation may feel lonely, but it feels reasonable. It matches everyday experience. You don't expect your coffee cup to tip over just because someone on the other side of the planet knocked theirs to the floor. Quantum mechanics, however, has a long history of taking ideas that feel reasonable and reducing them to ashes. In the 1930s, physicists uncovered something in the mathematics that simply shouldn't have existed: a flaw, a specter hiding in the equations. Under certain conditions, two particles could interact and then separate, yet somehow never truly become independent again. They remained linked, entangled. This connection isn't like a rope. It's not a signal being sent back and forth. It's far deeper than that. When two particles become entangled, they stop being two independent objects. Mathematically, they merge into a single system that happens to occupy two different locations. They share one wave function, one description, one existence. Picture this. Take two coins and spin them simultaneously. Then separate them. Carry one coin to the North Pole and the other to the South Pole. They are now as far apart as Earth allows, completely isolated. No contact, no communication. Now slam your hand down on the coin at the North Pole. It lands heads. Instantly, with no delay whatsoever, the coin at the South Pole lands tails. Every single time. If the northern coin is heads, the southern coin is tails. If one is tails, the other is heads. Perfect anti-correlation. This phenomenon is what Einstein famously called spooky action at a distance. He used the word spooky deliberately. It unsettled him. It violated the universe's speed limit. How did the coin in the South Pole know what happened at the North Pole at that exact moment? No signal had time to travel. No light beam, no radio wave, no physical influence could cross the planet that fast. It looked like magic, like telepathy. And worse, it suggested that space itself might be irrelevant. That distance, at least for these particles, didn't truly exist. Einstein despised this conclusion. He rejected it with intensity. He insisted that physics had to be wrong here. The universe, he believed, could not possibly operate in such an absurd way. There had to be a rational explanation, a classical explanation, something sane. And for a long time, most physicists agreed with him. Einstein proposed a rescue plan, a way to save locality and common sense. He argued that entanglement wasn't mysterious at all. It was simply a matter of missing information. He introduced the idea of hidden variables. Think of it like this. Imagine a pair of gloves. One left-handed, one right-handed. You place each glove into a separate box, you seal the boxes, you shuffle them, you give one box to a friend and keep the other. Then you fly to the moon while your friend stays on Earth. Your friend opens their box and finds a left glove. Instantly, they know you must have the right glove. Did the glove on the moon magically change the moment the box on Earth was opened? Of course not. No signal traveled faster than light. The gloves were already left and right from the beginning. The outcome was fixed. The only thing missing was knowledge. Einstein argued that entangled particles work the same way. When they are created, they make a secret agreement. One particle is assigned one outcome, the other is assigned the opposite. We can't see the assignment, so the result appears random, but it isn't. It's predetermined, written into the particles from the start. If Einstein was correct, then reality was safe. Locality survived. There was no instantaneous influence, no spooky action, just ignorance. We simply hadn't discovered the hidden variables yet. This explanation was elegant, logical, comforting, and for nearly 30 years, it dominated physics. Most scientists assumed Einstein had won. After all, why would nature rely on something bizarre when a simple classical explanation was available? Then, in the 1960s, an Irish physicist named John Stuart Bell decided to test that assumption. Bell asked a dangerous question. Is there any measurable difference between the glove story and true quantum entanglement? Is there an experiment that can distinguish hidden variables from genuine non-local connections? The answer turned out to be yes, and the clearest way to understand it isn't through equations. It's through a game that cannot be won in a classical universe, but is easily won in a quantum one. This is known as the magic square game. It sounds harmless, like a logic puzzle from a newspaper, but it is in fact a stress test for reality itself. Here's how it works. There are two players. Call them Alice and Bob. They are teammates. They win together or lose together. But during the game, they are completely separated, placed in different rooms. They cannot speak, gesture, text, or signal each other in any way. Each player receives a simple 3x3 grid, like a tic-tac-toe board. A referee asks Alice to fill in one specific row of her grid, using only ones and ones. Bob is asked to fill in one specific column of his grid, using the same values. There are strict rules. Alice must ensure that the numbers in her chosen row multiply to +1. Bob must ensure that the numbers in his chosen column multiply to 1. And here's the catch. The square where Alice's row and Bob's column intersect must contain the same number for both players. If Alice puts +1 in that square, Bob must also put +1. If they match, the team wins. If they don't, they lose. In a world governed by hidden variables, this sounds trivial. Alice and Bob could simply agree on a master grid beforehand, memorize it, use a fixed strategy. But when you actually analyze the constraints, something shocking appears. There is no possible grid that satisfies all the rules at once. No assignment of numbers can make every row multiply to +1, while every column multiplies to 1. It's logically impossible. In a purely classical universe, Alice and Bob can only come close to success. Even with the cleverest possible strategy, failure is inevitable. Their best outcome tops out at roughly 89%. Sooner or later, they lose. There is no escape. And this is where quantum mechanics delivers its knockout punch. The mathematics itself forbids perfection under classical rules. Absolute consistency is impossible. But the moment Alice and Bob are given a pair of entangled particles, something extraordinary happens. They stop losing. To see why the game is unwinnable for ordinary players, look closely at the structure. You're dealing with a grid of 9 squares. Each square must contain either a +1 or a -1. The constraints are strict. Every row must multiply to +1. Every column must multiply to 1. Try it yourself. Draw the grid. Start filling it in. You'll notice something irritating almost immediately. You can satisfy the first row. You can make the second row work. You can even get all the columns to behave. But when you reach the final square, the bottom right corner, everything collapses. To satisfy the row, you must write Pugs 1. To satisfy the column, you must write 1. You can't do both. The contradiction is unavoidable. This isn't a trick, it's a parity conflict. The rows demand an even number of negative signs. The columns demand an odd number. There is no way to reconcile those requirements. That means there is no master grid. No hidden cheat sheet Alice and Bob can memorize beforehand. No perfect strategy they can agree on before being separated. Eventually, the referee will ask for a row and a column that force a mismatch. In a classical universe, the ceiling is fixed. 89% is the best you can do. If Einstein was right, if particles are merely carrying pre-written instructions like gloves in boxes, then Alice and Bob must lose one game out of every 9. Logic demands it. Quantum mechanics does not. Now give Alice and Bob a quantum advantage. Instead of a memorized grid, they share entangled particles. 2 pairs in fact. Each player takes their particles into separate rooms. They do not coordinate. They do not plan. There is no script, no agreement about which numbers to write down. Their minds are blank. The referee asks Alice for a row. She doesn't consult a strategy. She measures her particles. The measurement depends entirely on which row she was asked to fill. The outcome is random. Spin up or spin down, which she translates into +1 or 1 and writes into the grid. At the same time, Bob is asked for a column. He measures his particles as well. His result is random too. But here's the miracle. Because the particles are entangled, their outcomes are not independent. When Alice measures her half of the system, Bob's half is instantly forced into a compatible state. Distance is irrelevant. Walls don't matter. Oceans don't matter. The particles are doing the coordination for them. The mathematics shows that if Alice and Bob follow this quantum procedure, the rules are always satisfied. The row multiplies to +1, the column multiplies to 1, and the shared square, the intersection, matches perfectly every single time. They win 100% of the games. They shatter the classical limit. They accomplish something that should be impossible. To an observer watching from the outside, it looks like cheating, as if there's a hidden cable under the floor, a secret channel of communication. But there is no cable, no signal, just the unsettling linkage imposed by quantum entanglement. Physicists have a name for this phenomenon. They call it quantum pseudo-telepathy. The term is precise. It captures the illusion perfectly. This is not real telepathy. Alice cannot use her particle to send Bob a message. She can't tell him what she ate for lunch. She can't transmit a warning or a stock tip. The randomness of the measurement makes that impossible. She has no control over the outcome, so she cannot encode information. And yet, it behaves like telepathy. Alice and Bob act as if they share a single mind. They coordinate responses in a way that requires information to be shared. If you saw 2 people in separate rooms, answering questions in flawless sync, you'd assume they were communicating. In the quantum world, they aren't. No information travels from Alice to Bob. It doesn't need to. They aren't holding 2 separate pieces of reality. They're holding 2 ends of the same structure. Entanglement effectively erases the space between them. For the purpose of the game, the distance is 0. This demolishes locality. Locality claims that objects can only influence their immediate surroundings. Pseudo-telepathy proves that the universe violates this rule. It shows that events here can have immediate consequences there, regardless of how far there is. At a fundamental level, the universe is not made of isolated components. It is a single, interconnected web. Pull one strand, and the entire structure responds. We don't notice because we're large, slow creatures. But particles feel it, and they exploit it to win. You might think this is just a laboratory curiosity, a trick that only works across a few meters of optical equipment. But scientists wanted to know how far this connection truly extends, so they tested it. In 2017, a team of Chinese researchers launched a satellite designed specifically to distribute entangled photons to Earth. One receiving station was located in the Himalayas. The other was more than 1,000 kilometers away. They ran the Bell test. The photons traveled through the vacuum of space and the atmosphere of Earth, and still, the entanglement held. The particles coordinated their states instantly across a continent. Then the tests became even more extreme. Physicists worried that perhaps the particles were somehow anticipating the detector settings, so they turned the universe itself into a random number generator. Telescopes were pointed at distant quasars, ancient galaxies billions of light years away. The color of the light arriving from those quasars determined how the measurements would be performed on Earth. This was the cosmic Bell test. It guaranteed that the measurement choices were fixed billions of years ago, long before Earth existed. Any conspiracy to fake entanglement would have had to originate before the planet was born. And the result? The entanglement still worked. Even when instructions came from the edge of the observable universe, particles on Earth behaved as a single system. The pseudo-telepathy remained intact. This proves that non-locality is not a laboratory glitch, not experimental noise, not a mathematical mistake. It is a property of the cosmos itself. It stretches across galaxies. It ignores distance. It disregards time. It binds the universe together in a way Einstein desperately hoped was not real. Space is enormous to us. To a quantum particle, it is effectively nothing. At this point, a reasonable question arises. If particles can coordinate instantly across the galaxy, why can't we use them to send messages? Why can't we build a quantum telephone? Why can't we communicate faster than light? If we could, Einstein's framework would collapse. Causality would break. Information could be sent backward in time. Reality would implode into paradox. This leads us to one of the most delicate compromises in physics. It's called peaceful coexistence, a fragile truce between two theories that fundamentally disagree. Quantum mechanics insists that connections are instantaneous, that distance doesn't matter, that events here and there update together. Special relativity insists that nothing outruns light, that space enforces separation, that causes precede effects. These ideas should annihilate each other, yet they coexist because of one narrow loophole: randomness. Return to Alice and Bob. Alice measures her particle. She gets a result, say, spin up. Instantly, Bob's particle becomes spin down. The update happens faster than light. The connection is real, but Alice cannot control her outcome. She cannot force spin up. She cannot encode a message. The result is fundamentally random, like flipping a coin. She has no way to say, spin up means hello. Bob faces the same limitation. When he measures his particle, he sees a random outcome. He cannot tell whether it reflects Alice's measurement or pure chance. All Bob sees is noise. The pattern only emerges later, when Alice and Bob reunite and compare their results. This is why information itself never travels faster than light. And this is how the universe maintains its most delicate compromise. It permits instantaneous correlation, but it blocks communication. Only the linkage establishes itself faster than light. The universe allows the eerie connection to exist, but it refuses to let us turn that connection into a telegram. It enforces the light speed limit by burying the mechanism behind a wall of pure randomness. It's as if reality is saying, yes, you can be connected, but no, you don't get to speak. It's a kind of cosmic censorship, a safeguard that prevents the laws of physics from collapsing into total chaos. So how are we supposed to interpret a universe where things are far apart and yet behave as if they're touching? One of the most brilliant and most controversial physicists of the 20th century, David Bohm, offered an answer. He suggested the problem isn't the particles. The problem is our picture of the universe. We assume space is an empty container and objects are separate items floating inside it. Bohm argued that this is the illusion. He used a famous analogy. Imagine an aquarium, a rectangular fish tank. Inside the tank, there is only one fish swimming around, but you cannot see the tank directly. Instead, you can only view it through two video cameras. One camera points at the front of the tank, the other points at the side. Each camera feeds a separate monitor in another room. Now you sit in that room and watch the screens. On one screen, you see a fish moving. On the other screen, you see what appears to be another fish moving. They don't look identical because the angles are different. On one monitor, the fish might appear long and narrow. On the other, short and wide. But as you watch, you notice something unsettling. Their movements are perfectly coordinated. When the fish on screen A turns slightly, the fish on screen B turns in a corresponding way. When the fish on screen A darts forward, the fish on screen B reacts instantly. If you didn't know the tank existed, you might conclude the two fish were communicating. You might invent an elaborate theory about faster-than-light signaling to explain the synchronized behavior. But the reality is simpler. There aren't two fish. There is one fish. The two fish are just two lower-dimensional projections of a higher-dimensional situation. Bohm argued the universe might be like that. We observe particles separated by vast distances. We see an electron here and another electron there and assume we're looking at two independent entities. But perhaps at a deeper layer, one we cannot directly access, they are not truly separate at all. Maybe space itself is the projection. Maybe the universe behaves like a hologram. In a hologram, every fragment contains information about the whole. Cut it in half and you don't get half an image. You get two smaller versions of the entire image. If reality is structured that way, then entanglement isn't mysterious. It's expected. Things appear connected because they were never fully disconnected to begin with. The separation is a perspective trick, a limitation of the screens we're forced to look at. We keep staring at the monitors instead of seeing the tank. Now take that idea and apply it to yourself. Not to photons in a lab, but to the atoms in your body, the neurons that generate your thoughts, the air moving through your lungs. We know entanglement can occur when particles interact, when they collide, or when they are born from the same event. They form a bond that distance can't erase. So consider the history of the universe. Run the clock backward, past modern civilization, past the Roman Empire, past dinosaurs, past the formation of Earth, past the birth of the sun, all the way back to the beginning. At the initial moment, all matter and energy in the cosmos was compressed together. Every electron, every quark, every photon, everything that would later become you, and everything that would later become the most distant galaxy, was once part of the same violent, unified state. Everything touched everything. Everything interacted. If entanglement is real, and if these links can persist in principle, then strictly speaking, nothing in the universe is truly isolated. The particles in your left hand once jostled against the particles that now make up a black hole in Andromeda. The atoms in your eyes were once tangled in the same early cosmic storm as atoms now burning in the core of a dying star billions of light years away. The connection is not local, it's universal. Physicists sometimes call this the universal wave function, the idea that there are no truly separate systems. There is only one system, the universe as a whole. You are not an observer standing outside it, looking in. You are part of the wave. You are a ripple inside the ocean. That sounds poetic, but it's also unsettling because it implies privacy is an illusion. Isolation is a convenient story. On the quantum level, you are always, in some sense, in contact with the farthest reaches of the cosmos. Every movement you make, every thought you form, every breath you take, it's all embedded in a single description that, at least mathematically, includes everything at once. We like to imagine ourselves as independent agents, separate individuals with clean boundaries. But quantum mechanics suggests those boundaries are not sharp. The border between you and the rest of reality is not a brick wall. It's a dotted line. And under certain conditions, that dotted line can vanish entirely. We have already dismantled time. We have already undermined space. We have stripped away the comfort of distance. But there is one last refuge we still cling to. One final shield that protects our sanity. The belief that there is a single objective truth. Look at what we've done so far. The damage is serious. We began with a comforting picture. A map where time runs forward like a river. Where objects stay put. Where separation is real. Where the world is stable and obvious. That map is now shredded. We've seen experiments that suggest the future can reach back and shape the past. We've seen two distant objects behave like one system. We've learned that what feels solid is, underneath, a shifting web of probabilities and invisible linkages. And yet, through all of this, we've held onto one desperate hope, that facts remain facts. We assume that even if the mathematics is strange, there is still one shared reality. If I see something happen, you should see the same thing happen. Truth should be public. If a light is on, it's on for everyone. If a cat is dead, it's dead for everyone. If a measurement happens, its result should be fixed. a single outcome all observers can agree on. That assumption is the foundation of science. It's also the foundation of sanity. Without shared facts, we're not living in a common world. We're living in private dreams, hallucinations talking to hallucinations. But what if even that last pillar collapses? What if quantum mechanics has one final weapon? A thought experiment designed to destroy the very notion of objectivity. We are now approaching the final paradox. It's the one physicists argue about with genuine anger. The one that turns conference halls into battlegrounds. It's called Wigner's Friend. And it doesn't just question physics. It questions whether a shared world exists at all. It asks a simple, terrifying question. Can you and I observe the same event, report two completely incompatible realities, and both be correct? If the answer is yes, then the loneliness becomes absolute. The universe isn't a public stage. It's a private screening, and you may be the only audience member. Get ready. We're about to pull the last brick out of the wall. To understand this final collapse, we have to return to the most famous cliché in physics, the cat. You know the setup. Schrödinger imagines a cat sealed in a steel box. Inside is a radioactive atom, a detector, and a vial of poison. The atom has a chance to decay. If it decays, the poison is released. The cat dies. If it doesn't decay, the poison stays sealed and the cat lives. Quantum mechanics says that until the box is opened, the atom is in a superposition, decayed and not decayed, which means the poison is released and not released, which means the cat is both alive and dead, a bizarre overlap of mutually exclusive outcomes. Most people treat this as a joke, or at most a metaphor for tiny particles. We reassure ourselves, obviously a real cat can't be dead and alive. A cat is big, warm, full of motion and complexity. It interacts with its environment constantly. Air molecules bounce off it. Heat leaks. The environment measures the cat long before anyone opens the lid. The superposition collapses on its own. We tell ourselves quantum weirdness stops at the microscopic scale. Cats, tables, and people belong to the sane world. But in 1961, Eugene Wigner decided to remove that comfort. Wigner was no eccentric outsider. He was a Nobel Prize winner, one of the architects of modern physics, and he noticed a loophole in the cat story, a gaping hole nobody wanted to stare into. The cat can't report its experience. It can't write a lab notebook. It can't testify about what happened inside the box. We assume the cat knows whether it's alive, but we can't ask it. So Wigner replaced the cat. He put a person inside the sealed system, a human observer, a friend. Call him the friend. Wigner places this friend inside a perfectly isolated laboratory. Inside the lab is a quantum device to measure, maybe a particle spin, maybe a photon's polarization. There are two possible outcomes, up or down, heads or tails, plus or minus. The friend is a trained scientist. He has eyes, a brain, a notebook. He observes the result and writes it down. He experiences a definite outcome. Then Wigner seals the lab completely. No light in, no sound out. No information passes through the walls. Wigner stands outside in the hallway and waits. He knows the measurement is happening inside. He knows the friend is looking at the system. He knows the friend is recording a result. Now comes the question that breaks everything. Before Wigner opens the door, how should he describe the state of the entire laboratory? This isn't a word game. It's a direct test of what quantum mechanics actually claims. According to the strict logic of the Schrödinger equation, an isolated system evolves smoothly and remains in superposition until it interacts with something external. And that is how the universe keeps its most fragile equilibrium intact. It permits instantaneous correlation, but it denies communication. The connection locks in faster than light, but nothing usable is transmitted. Reality allows the eerie linkage to exist, yet it refuses to let us turn that linkage into a telegram. It protects the speed of light boundary by burying the process behind an impenetrable wall of fundamental randomness. It's as if the universe is saying, I'll let you be connected, but I will not let you speak. A kind of cosmic censorship, a safety valve, a way to keep physics from dissolving into total lawlessness. So how do we interpret a universe where two things are far apart and still behave as if they're pressed together? One of the sharpest and most controversial minds of the 20th century, David Bohm, argued that our mistake isn't in the particles. Our mistake is in the picture we carry in our heads. We imagine space as an empty stage and objects as separate actors standing on it. Bohm suggested that separation might be the illusion. He offered a famous analogy. Picture an aquarium, a rectangular fish tank. Inside it, there is only one fish swimming around, but you are not allowed to look directly at the tank. Instead, you can only observe it through two cameras. One camera faces the front of the tank, the other faces the side. Each camera feeds a separate monitor in another room. You sit in that room and watch both screens. On screen A, you see a fish gliding left and right. On screen B, you see what appears to be another fish moving in a different shape. One looks long and slender. The other looks short and wide. They don't match perfectly because you're seeing different angles. But then you notice something unsettling. The movements are synchronized. When the fish on screen A turns slightly, the fish on screen B turns in exactly the corresponding way. When the fish on screen A darts forward, the fish on screen B reacts instantly. If you had no knowledge of the tank, you might conclude the two fish are exchanging signals faster than light. You might build elaborate theories to explain their coordination. But the truth is simpler. There are not two fish. There is one fish. The two images are merely projections, lower dimensional shadows of a single higher dimensional reality. Bohm argued that the universe might work the same way. We observe particles separated by massive distances and assume they are independent objects. We see one electron here and another electron there, and imagine two separate beings. But perhaps at a deeper level, we cannot directly perceive those two particles are not truly separate. Maybe space is the projection. Maybe the separation is a byproduct of how we're forced to observe. Maybe reality behaves like a hologram. In a hologram, every piece contains the information of the whole. Break it, and you don't get half a picture. You get two smaller versions of the entire picture. If the universe has that kind of structure, then entanglement isn't mysterious. It's normal. Things appear connected because they were never fully disconnected. The distance exists on the screen, not in the underlying tank. We keep staring at the monitors. We never see the deeper geometry. Now bring that thought closer. Not to photons on an optical table, but to you, to the atoms in your skin, the neurons firing in your brain, the air filling your lungs. We know entanglement forms when particles interact, when they collide, when they are created together, when their histories overlap. They forge a bond that distance cannot simply sever. So consider the history of the cosmos. Rewind the timeline. Past cities, past empires, past dinosaurs, past Earth's formation, past the sun's birth, all the way back. At the beginning, everything was compressed together. Every quark, every electron, every photon, everything that would eventually become you, and everything that would eventually become the farthest stars, existed in a single packed violent state. Everything touched everything. Everything interacted. If entanglement is a genuine feature of nature, and if these relationships can persist in principle, then, in a very literal sense, the entire universe remains entangled with itself. The particles that make up your left hand once collided with particles that now orbit in a black hole. The atoms in your eyes once shared a primordial intimacy with atoms now burning in the core of a star billions of light years away. The web is not local, it's universal. Physicists sometimes describe this with the idea of a universal wave function, the notion that there are no truly isolated systems. There is only one system, the universe itself. You are not a spectator standing outside it. You are part of the wave, a ripple inside an ocean so vast you can't see the shoreline. It sounds beautiful, but it also feels invasive because it implies that privacy is not fundamental. Isolation is a convenient story. At the quantum level, you are never fully separated from the farthest parts of existence. Every motion you make, every breath you take, every thought that forms, all of it lives inside a single mathematical description that, at least in principle, includes everything at once. We like to think of ourselves as independent agents with clean borders. Quantum mechanics suggests those borders are fuzzy. The line between you and everything else is not a concrete wall. It's a dotted boundary. And under the right conditions, even that dotted boundary can dissolve. At this point, we've already taken a wrecking ball to time. We've weakened space. We've removed the comfort of distance. But there is still one final protection we cling to for sanity: the belief that there is one objective truth. Look at the wreckage so far. It's not small. We began with a comforting model: time as a forward river, objects as stable things, distance as separation, reality as public and shared. That model is now shredded. We've seen that future choices can align with past outcomes in ways that feel like influence reaching backward. We've seen two objects act like one across unimaginable distances. We've watched solid reality reveal itself as probabilities stitched together by invisible constraints. And still, through all of this, we've held on to one desperate hope: facts remain facts. Even if the math is bizarre, we assume there is still one shared world. If I see something happen, you should see the same thing happen. Truth should be public. If a light is on, it's on for everyone. If a cat is dead, it's dead for everyone. If a measurement happens, the outcome should be fixed. One result carved into reality, available for all observers to agree on. That assumption is the foundation of science. It's also the foundation of sanity. Without shared facts, we're not living together in one world. We're isolated in private dreams, hallucinations conversing with hallucinations. But what if that last pillar is about to collapse too? What if quantum mechanics contains one final weapon, a scenario that attacks the very notion of objectivity? We are entering the final paradox, the one that sparks real arguments, the one that makes researchers raise their voices in conference halls. Wigner's friend. It doesn't just question the laws of physics. It questions whether a shared world exists at all. It asks a simple, terrifying question: can two observers witness the same event, report two mutually exclusive realities, and both be correct? If the answer is yes, then the loneliness becomes absolute. The universe is not a public stage. It's a private screening. And you may be the only one in the theater. So let's pull the last brick. To understand this collapse, we have to return to the most famous cliché in physics: Schrödinger's cat. You know the story. A cat sealed in a box, a radioactive trigger, a vial of poison. The atom may decay or it may not. If it decays, the poison is released and the cat dies. If it doesn't, the cat survives. Quantum mechanics says that before the box is opened, the atom is in a superposition, decayed and not decayed, which means the poison is released and not released, which means the cat is dead and alive at the same time. Most people treat this as a joke, or a metaphor meant only for tiny particles. We tell ourselves, obviously a real cat can't be both dead and alive. A cat is large, warm, complex. It interacts constantly with its environment. Air molecules bounce off it. Heat leaks. The environment measures the system long before we lift the lid. Decoherence destroys the superposition. We comfort ourselves by saying quantum madness stays microscopic. Big things, cats, tables, human beings, live under sane rules. In 1961, Eugene Wigner attacked that comfort. Wigner was no fringe thinker. He was a Nobel Prize winner and a central architect of 20th century physics. He looked at the cat setup and saw a loophole nobody wanted to face. The cat can't report what it experienced. It can't write a lab notebook. It can't testify about what happened inside the box. We assume it knows whether it lived or died, but we can't interrogate it. So Wigner replaced the cat. He put a human observer inside the box, a friend. Wigner imagines a sealed laboratory, perfectly isolated. Inside is a quantum system to be measured, perhaps a photon polarization, perhaps an electron spin. There are two possible outcomes, up or down, plus or minus. The friend is a capable scientist. He looks at the instrument. He sees an outcome. He writes it down. He forms a memory. Consciousness is involved. Then Wigner seals the lab completely. No light enters. No sound escapes. No information leaks. Wigner remains outside in the hallway. He knows a measurement is being performed inside. He knows the friend is recording a definite result. Now comes the question that shatters reality. Before Wigner opens the door, how should he describe the state of the entire lab? This isn't wordplay. It's a direct consequence of the Schrödinger equation. If the lab is perfectly isolated, then from Wigner's perspective, the lab is one quantum system. The equipment, the air, the walls, and the friend. All made of atoms, all governed by the same wave function. And that means, from Wigner's standpoint, the friend has not reached a single definite outcome yet. The friend is in superposition. The friend saw up and saw down. The friend wrote up and wrote down. Two versions of the friend coexist in the sealed room at the same time. It sounds absurd, but the math demands it. And that's just the stage setting. The real horror begins when you ask the question nobody wants to answer. Who is right? Freeze the moment and view it from both perspectives. First, step inside the lab. Become the friend. You're at the table. You look at the detector. You see the signal. A clear outcome, say spin up. It feels concrete. It feels undeniable. You feel the moment in your body. You pick up your pen and write spin up in your notebook. You look at your hands. Solid. You look at the walls. Stable. You do not feel like a ghost. You do not feel split. You do not feel suspended between realities. From your point of view, the wave function has collapsed. The uncertainty is gone. The probability has hardened into a fact. The event is now history. It happened minutes ago. Done. Now slide through the wall and stand in the hallway as Wigner. You haven't opened the door. You're holding your clipboard. You're describing the lab using quantum mechanics. The lab is isolated. No information has escaped. So from your perspective, nothing has collapsed. In your equations, the lab is still a superposition. Friend saw up plus friend saw down. Both terms exist. They coexist. They can, in principle, interfere. If you had the power to perform a giant interference experiment on the entire room, you could reveal that the lab behaves like a wave containing both outcomes. So from your point of view, the measurement hasn't happened yet. And that is the paradox. The friend says, the measurement happened. Wigner says, it didn't. The friend says, reality is spin up. Wigner says, reality is spin up plus spin down. In classical physics, this cannot occur. Reality is supposed to be objective. If a tree falls and one person hears it, it fell. Another person 5 miles away might not hear it, but the event still belongs to the same timeline. There is one book of facts. You might not have read page 10 yet, but page 10 doesn't change depending on who holds the book. Here, page 10 does change. The factual status of the event is different for the friend and for Wigner. The friend claims a definite state exists. Wigner claims the definite state does not exist, not for him. And the truly disturbing part is that quantum mechanics offers no rule that automatically crowns one viewpoint as the correct one. It does not declare the inside observer the winner. It does not grant the outside observer priority. It treats observers symmetrically. That symmetry detonates into a logical contradiction. Because when Wigner finally opens the door, he will see a definite outcome in the notebook. He will see spin up written clearly. The wave function will collapse for him at that moment. But then you must ask the forbidden question. What was the friend 1 second before the door opened? Was the friend already living in a definite reality, experiencing a memory and certainty? Or was the friend suspended in an unresolved mixture of realities until Wigner looked? Does the friend only become real when Wigner observes him? And if so, does Wigner only become real when someone else observes him? Where does it stop? Who is the final observer? For decades, many physicists tried to sweep this aside. They called it philosophy. They called it distraction. They said, "You're thinking too hard. Go do real calculations." They also insisted the paradox would never occur in practice. You can't isolate a human being perfectly. Humans radiate heat. Humans breathe. Humans interact with the environment. The wave function collapses naturally. The paradox stays on paper. They thought they were safe. They weren't. Technology improved. Lasers became sharper. Detectors became faster. Experimental control became more brutal. And in 2019, researchers decided to stop treating Wigner's friend like a thought experiment and force it into the laboratory. They didn't use a human friend, for obvious reasons. No ethics board is signing off on locking a grad student in a sealed lab and potentially breaking the definition of their reality. Instead, they built an analog using photons. They designed a setup where one photon played the role of the friend, an internal observer, by measuring the polarization of another photon and recording that outcome in its own quantum state. If the target photon was vertical, the friend photon shifted into one state. If it was horizontal, the friend photon shifted into another. That interaction created a record. A measurement had happened inside the system. Then they introduced external detectors, playing the role of Wigner, devices that could measure the entire friend system from the outside without directly learning which outcome occurred, and could test whether the larger system still behaved as an uncollapsed wave capable of interference. They ran the experiment again and again, collecting data, looking for one specific thing: evidence that the internal observer could have a definite fact while the external observer still described an indefinite reality. To test this, they used a Bell-type inequality, but not the standard one. A specialized inequality derived by Czaslaw Bruckner, designed for exactly this scenario. It assumes something extremely important. Observer-independent facts exist. That there is a single objective reality beneath all perspectives. If that assumption is true, the inequality must hold. There is a limit to how incompatible different measurements can be, but the inequality was violated. Not bent, not grazed. Violated. The numbers refused to stay within the boundary demanded by objective, observer-independent facts. The data implied that the internal observer and the external observer could not be combined into one consistent story. The friend had a fact. Wigner had a fact. And those facts could not be stitched together into a single universal narrative without contradiction. It was a bombshell. The results were published in a top journal. Headlines screamed that quantum physics had proven objective reality doesn't exist. And for once, the dramatic headlines weren't purely nonsense. The implication was stark. At the quantum level, there is no single God's eye description of the world. No master ledger where all true events are recorded in one coherent timeline. There are only perspectives, local frames, partial accounts. What is true for you inside the lab is not necessarily true for me outside it, and both can be valid. Let that sit in your mind. Really sit there. This isn't about preferences or interpretations. Not, I like vanilla, you like chocolate. Not a trick of perception like a dress that looks one color to one person and another color to someone else. This is about physical events. Did the atom decay or not? Is the light on or off? Science has always relied on one massive assumption: observer-independent facts. The world is out there, and we uncover it. If humanity vanished tomorrow, stars would still shine, planets would still orbit, atoms would still collide. Facts would remain facts. Wagner's friend attacks that foundation. It suggests a fact is not a public object. It is a relationship, a private link between an observer and the system observed. My measurement produces my reality. Your measurement produces yours. Until we interact, those realities are not obligated to match. That idea opens the door to a philosophical nightmare: solipsism, the suspicion that only your mind is real and everything else is projection. We normally dismiss solipsism as pointless and self-indulgent. Of course you're real. I can touch you. But quantum mechanics whispers something darker. Maybe we are more isolated than we think. If you can inhabit a world where the spin is definite, and I can inhabit a world where the spin is still indefinite, are we truly in the same universe? Or are we each trapped inside personal bubbles of reality? Bubbles that overlap sometimes, but never fully fuse. Now think about what this does to truth. We build courts around truth. We fight wars over truth. We cling to the belief that there is one chain of events that happened, one objective story. If physics says truth is observer relative, the foundation of shared existence develops cracks. It hints that at the deepest level, we are alone, navigating a landscape of personal facts. Maybe when I look at you, I force you into states that answer my questions. Maybe when you look at me, you force me into states that answer yours. We aren't merely discovering each other, we are generating each other. That's the ultimate sting of Wigner's friend. It suggests the universe is not a rigid warehouse filled with objects. It is a participatory game, and the rules of the game don't allow you to stand outside it. You must play, and the move you make determines the board you see. So how are we supposed to live with this? Physicists have spent decades trying to escape this trap, trying to construct an interpretation that preserves coherence without destroying our sanity. The first major attempt is the most famous and the most radical: the many worlds interpretation. In the 1950s, a graduate student named Hugh Everett III looked at quantum mechanics and decided to take it literally. He asked, what if the wave function never collapses? What if probability never disappears? What if every possible outcome actually happens? Under many worlds, Wigner's friend is resolved by multiplying reality. When the friend measures the particle, the universe branches, like a tree splitting. In one branch, the friend sees spin up. In another branch, the friend sees spin down. Both branches are real. Both versions of the friend exist. They just can't communicate across the split. Now consider Wigner in the hallway. In this interpretation, Wigner isn't looking at a single friend floating in a strange blur. He's standing at the trunk of the branching tree before he personally becomes entangled with a specific branch. When he opens the door, he doesn't collapse anything. He simply joins the branching. One version of Wigner opens the door and finds the friend with spin up. Another version opens the door and finds the friend with spin down. Each Wigner experiences a consistent reality in their branch. Objectivity is restored, but at an enormous price. There is no single unique outcome. Every outcome occurs. The friend is right in his branch. Wigner is right in his branch. The contradiction vanishes because there is no single world where both incompatible facts must coexist as one story. But the cost is terrifying. Reality becomes infinitely heavy. Every interaction, every photon scattering off a leaf, every atom shifting, every microscopic event causes the universe to split into more branches. The cosmos becomes an endlessly expanding labyrinth of histories. It sounds like science fiction. It sounds like a multiverse movie. Yet many serious physicists argue it's the cleanest way to honor the math without inventing a magical collapse rule. If you refuse to add special exceptions, many worlds becomes hard to avoid. And if it's true, then there are countless versions of you living countless lives. In one branch, you clicked away from this video 10 minutes ago. In another, you never found it. In another, you became a physicist. In another, you died before you reached this sentence. In many worlds, the Wigner's friend paradox disappears because the conflict is an illusion produced by trying to force a single storyline onto a reality that branches. The friend sees one outcome because he's already in a branch. Wigner sees a blur because he hasn't joined a branch yet. Once he opens the door, he becomes entangled with the result. He slides into a specific history. No contradiction remains, only infinite unfolding. It's a clean solution, and it's also a nightmare. Because it implies that being unique is basically a bedtime story we tell ourselves. It suggests that choices don't erase possibilities. They just steer you into one hallway while countless other hallways remain, each containing a version of you that you will never meet, never hear from, never visit. And there's another way out of this puzzle, one that doesn't demand an infinite explosion of universes, but it demands a harsher payment. It asks us to surrender the idea that physics is actually describing reality in the first place. This approach is called quantum Bayesianism, or cubism. The people who support it argue that we've been committing a category mistake for 100 years. We look at the wave function, the math that predicts what a particle might do, and we treat it like a physical thing, like it's an actual wave out there in the world, rolling around like surf, waiting for us to measure it. Cubism says, stop. That's the wrong picture. The wave function isn't out there. It's in your head. It isn't a description of what the atom is. It's a description of what you believe about the atom based on what you currently know. It's a tool, a decision guide, a way of assigning odds to possible outcomes. Think about poker. You're holding two cards. You estimate your chances of winning. Those chances aren't a physical object hovering above the table. They're not part of the furniture of the universe. They're your personal state of uncertainty and expectation. If you secretly peek at your opponent's hand, your odds change instantly. But nothing about the physical cards changed. The table didn't change. The room didn't change. Only your information changed. So your wave function updated, but your opponents didn't, because your opponent doesn't know what you learned. Now apply that logic to Wigner's friend, and the paradox evaporates. Why do Wigner and the friend describe the lab differently? Because they possess different information. The friend is inside the room. He has seen the cards. He has the outcome in his notebook. From his perspective, the odds are no longer odds. They're certainty. Wigner is in the hallway. He has not seen the cards. From his perspective, assigning a 50-50 state is the rational move. Both are correct, not because reality is splitting, but because they're not actually describing the same thing. They're describing their own best bet about what they will experience next. In Cubism, physics is not a public inventory of facts about the room. Physics is a rule book for how an agent should update beliefs when interacting with the world. No contradiction, because the theory was never meant to be a God's eye photograph of reality. It's a user manual for making decisions under uncertainty. Sounds clean. Practical. A neat escape from the multiverse. But look at what it quietly steals from you. It steals the world. Because if physics is just a betting framework, then what are you placing bets on? What exists when nobody is betting? Is there a reality out there? Or is there only experience and predictions about future experience? Cubism shifts the goal of science away from objective truth. It says the purpose of science is survival and navigation, how an agent stays coherent inside a chaotic universe. It drags everything back to the first-person perspective. It insists you cannot remove yourself from the equation. You're not an impartial camera recording nature. You're a participant, holding a ticket, taking risks, updating beliefs. The laws of physics become house rules. They tell you how to play. They don't tell you what the game is made of. For many scientists, that's unacceptable. It feels like surrender, like saying reality is just mind stuff. But the Cubists shrug and say, fine, show us your objective facts. Show us the observer-independent story. You can't, because Wigner's friend and the related experiments are exactly what crushed that dream. So if you reject the multiverse, and you reject the physics as betting view, there's a third door. And most physicists don't even want to touch the handle. The door marked consciousness. Since the beginning of quantum mechanics, this idea has been whispered in the background. One of the strongest voices was John von Neumann, one of the greatest mathematicians ever to walk the planet. He followed the measurement chain all the way through. A particle hits a detector. The detector triggers a signal. The signal runs through a wire. The wire moves a needle or flashes a light. Photons from that display hit your retina. Your retina sends impulses into the brain. Von Neumann pointed out something unsettling. At every step of this chain, the system is still physical interactions. Atoms hitting atoms, fields coupling to fields. There's no obvious physical law that says, collapse happens here. There's nothing sacred about the retina, nothing magical about the screen. The equations can keep going. So he argued it must stop somewhere. And the one thing that doesn't obviously belong to the same physical category is subjective experience, the raw fact of awareness. That leads to a shocking conclusion. Consciousness is not just a byproduct that shows up after matter does its thing. Consciousness is the final cut that turns possibility into a single actual event. In this view, the universe without observation remains a kind of unresolved ghost, an ocean of probabilities that hasn't settled into a definite story. In Wigner's friend, the answer becomes straightforward. Who collapses the wave function? The friend does, because the friend is conscious. The moment the friend experiences the result, the uncertainty ends. The superposition dies. And Wigner is wrong to treat the lab as a wave, because he's treating a conscious observer as if he were just another chunk of hardware. Just atoms in a box. This idea didn't die. It keeps resurfacing, especially in modern discussions about the mind. Roger Penrose, for example, has argued that consciousness might involve quantum processes in brain structures called microtubules, an approach often referred to as orchestrated objective reduction. He's trying to connect the biology of the brain to the deeper geometry of the universe itself. If anything like that were true, we aren't just spectators. We are part of the mechanism that produces definite reality. That's flattering, almost dangerously flattering. It turns the mind into something like a cosmic lever. But it also creates a nasty set of questions you can't dodge. Does a dog collapse the wave function? A fly? A bacterium? Where do you draw the line? If all humans vanished, would the universe drift back into a haze of unresolved probabilities? Would the moon disappear without an observer? Einstein mocked that idea with his famous question. But under the pressure of Wigner's friend, it stops being a joke and starts looking like a real scientific problem. There's one more way to see all of this. One that preserves the cold results of the experiments without inflating reality into endless universes or turning physics into pure psychology. It's called relational quantum mechanics, proposed by Carlo Rovelli. Rovelli argues that we keep asking the wrong question. We keep asking, what is the state of the particle? As if the particle carries a state all by itself, like an object carrying a label in its pocket. Rovelli says that picture is false. Objects do not have properties in isolation. They only have properties relative to something else. Think about speed. If I ask, how fast are you moving? You can't answer without asking, relative to what? Relative to your chair, you're basically still. Relative to the Earth's rotation, you're moving fast. Relative to the sun, you're moving insanely fast. All of those answers can be true at the same time. Speed isn't a property of you alone. It's a property of the relationship between you and a reference frame. Rovelli claims quantum properties work the same way. Position, momentum, spin, energy, even having a definite outcome. None of it is absolute. It's all relational. So in Wigner's friend, the paradox only appears because we assume there must be one absolute account of what happened inside the lab. Relational quantum mechanics says there is no absolute account. For the friend, the particle is spin up. That is true relative to the friend. For Wigner, the lab is still in superposition. That is true relative to Wigner. No contradiction, because they are not describing the same relationship. They are reporting facts that exist only within specific interactions. Reality, in this view, is not a warehouse of objects. It's a network of interactions. Not things, connections. And here's the more intimate way to picture it. A kiss does not exist on your lips alone, or my lips alone. A kiss exists only in the interaction between us. It's a relational event. Rovelli is basically saying the universe is built out of those relational events. When you measure an electron, you establish a relationship, and in that moment, a fact becomes real for that relationship. This rescues us from solipsism. You're not alone in a private hallucination, but it also denies the fantasy that we are uncovering a fully pre-written universe. Instead, the shared world we call objective reality is something we stitch together through interaction, through communication, through comparing records, through forming a consistent story across many relationships. The public world isn't a rock. It's a negotiated agreement, a delicate consensus assembled moment by moment. And that brings us to the bottom of the rabbit hole. We've torn apart time. We've weakened space. We've attacked the idea of observer-independent truth. What's left is a universe that feels like a floating web of probability and relations. It's unsettling. It can feel like the floor vanished, but it can also feel strangely beautiful, because it suggests reality isn't a machine that runs without you. It's more like a living composition, and you're one of the instruments inside it. So now we have to look at the wreckage and ask what still stands. When we began, you were standing on what felt like solid ground. Hard objects, a one-way river of time, safe distance in space, truth that was the same for everyone. Now look where we are. The delayed choice quantum eraser took the timeline and twisted it into something that behaves like a knot, hinting that the future can align with, almost select, how the past is allowed to appear. Quantum pseudo-telepathy took the map of space and ripped it in half, showing that separation can be a surface illusion, while deeper correlations remain intact across huge distances. And Wigner's friend took the very idea of a single shared reality and shattered it, showing how facts may depend on the observer's relationship to the system. The floor is gone. The walls are gone. The ceiling is gone. We're suspended in a universe where time can be treated symmetrically, where space can behave non-locally, where truth can be relational rather than absolute. This is usually the point where the human brain tries to slam the door shut. We want Newton back. We want the comfort of a clockwork universe. We want to pretend the coffee cup is just a cup and nothing else. But the evidence doesn't let us rewind. The experiments happened. The numbers don't care about your comfort. And once you've seen the machinery behind the curtain, you can't pretend you didn't. So we need a new way to stand in this strange void without collapsing into panic. There was one man who saw this kind of universe coming. His name was John Archibald Wheeler, mentor to Feynman, the physicist who helped coin black hole, and a thinker who kept pushing physics toward the edge of philosophy. In his later years, Wheeler proposed an idea that ties all these paradoxes together. He called it the participatory universe. He said we've been telling the story backward. We imagine the universe begins with the Big Bang. Then matter forms stars, stars form planets, life emerges, and finally consciousness appears at the end like a late audience member watching the show. Wheeler said, "No, we are not the audience. We are part of the show." He used an analogy based on the party game, 20 questions. Normally, someone leaves the room, the group chooses a secret word, and when the person returns, they ask yes/no questions to guess it. The word exists before the questions. The answers are fixed. That's the classical universe. Reality is pre-written, and measurement merely reveals it. But imagine a twisted version of the game where the group doesn't pick a word at all. They decide they will answer each question in a way that stays consistent with previous answers, but without committing to a specific word until the end. Is it alive? Someone says, "No." Now the hidden word must be non-living. Is it big? Someone says, "Yes." Now it must be big and non-living. The questions continue, narrowing the space of possibilities. Eventually someone asks, "Is it a cloud?" And the group realizes cloud fits everything so far. They answer, "Yes." In this version, the word wasn't waiting in the room before the questions. The word was created by the questions. Wheeler said quantum mechanics is doing something like that. The electron doesn't have a position until we ask where it is. The photon doesn't have a path until we ask which route it took. The universe doesn't have a fully settled history in the way we intuitively imagine, until observations carve out a consistent narrative. This is what Wheeler called it from bit. The idea that physical reality, particles, fields, even space-time, derives its meaning and its definite form from binary outcomes, from yes/no answers produced by interaction and measurement. We're not simply discovering a pre-made world, we're extracting reality from silence. Wheeler drew a picture that became famous, a giant U-shaped diagram. One arm of the U is the beginning, Big Bang, early universe, the growth of structure. The curve runs down through galaxies, stars, planets, chemistry, life. Then the other arm rises back up to an eye at the end, an eye looking back at the beginning. That eye is us, star stuff that woke up, matter arranged into nervous systems that turned around and asked where it came from. Wheeler was suggesting something deeply unsettling. The universe is a self-excited loop. The cosmos creates observers, and observers help define the cosmos. The present participates in making the past a definite story. That idea echoes the delayed choice experiments. It echoes why later measurement choices can determine what sort of pattern is allowed to appear. It echoes why observation seems structurally involved, not merely optional. Science tried for centuries to scrub the human element out of the equation, to be purely objective, as if we weren't here. Quantum mechanics grabbed us and dragged us back onto the stage. It says, you don't get to leave. You matter. You are part of the structure through which the probabilistic fog sharpens into something definite. And that terrifies people. It terrified Einstein. It made Schrödinger uneasy. It makes modern physicists argue until their voices crack, because we love the mechanical universe. It's comforting. If we are small cogs, we aren't responsible. If reality is objective, we just measure it and go home. But if the participatory view is even partly true, then reality isn't just there. Reality is something that emerges through interaction. It's something we help maintain. And that is an uncomfortable responsibility. The uneasy feeling that the lights stay on because someone is watching. The primal fear that the only thing holding back the dark is the beam of your flashlight. But there's another way to see the same thing. Not as horror, as power. If our questions and interactions matter, then we are not prisoners of a rigid script. We aren't helpless passengers in a frozen block universe. We aren't isolated specks in a meaningless void. We are woven into the deepest logic of existence. We are one of the ways the universe becomes aware of itself. So the next time you wake in the middle of the night, or walk into a dark room, or stare up at the stars, ask yourself something that feels almost forbidden. Are those things simply waiting out there, fully defined, indifferent to you? Or are they waiting for you to participate? To make them real, in the only way reality ever becomes real. The science isn't finished. The paradoxes aren't all neatly resolved. The old debate between Einstein and Bohr still echoes. But the evidence keeps stacking, and it keeps pointing toward the same unsettling conclusion. The world is not what your instincts claim. It is stranger, softer, and far more intimate. You might try to forget this. You might try to return to the solid comfort of everyday life, to convince yourself that the cup on your table is just a cup. And maybe, honestly, for sanity, that's not a bad strategy. But somewhere deep in your mind, you'll remember what the experiments imply. Behind the curtain of common sense, there is a sea of probabilities, a web of connections, and a question mark hanging over everything. And the universe, whatever it truly is, seems to be waiting to see what you choose to look at next.